Welcome to Rapid CD. So in Rapid CD, this is the home screen. There are three modules. Number one is the general analysis, which is used for understanding or comparing the CD spectra of multiple samples. The second is the thermal analysis. Suppose if you want to understand know the melting temperature and you have multiple temperature recorded for a protein or a peptide, then you can do thermal analysis. And this is the reversibility. In today's video, we are going to see the general analysis tab. So here we come in this green button and we click here in the general analysis. So we can see here the first option which shows the experimental setup. We can select increase the number of samples we want or also decrease it. Now here we can see an option known as the common and individual, and these are the blank. So suppose I have three of my samples or two of my samples and both of them are taken in phosphate buffer, and phosphate buffer we have also recorded as a blank. Then we can select it as common and then we can upload from here the phosphate buffer text file. However, if we want to compare a protein or a peptide taken in phosphate buffer and the other one is taken in SDS or in some other solvent, then the blank for each of them are different. Then we can go here and select individual. So once we do that, what we will see. So firstly, I would like to show you in case of common. So in case of common, when we have uploaded one blank, for example, I will click here and I will upload a blank, for example, phosphate buffer. Now, if I go here in my sample, here I can upload the file of my sample, like upload text file. Make sure that you are uploading the text file only, no CSV, no machine binary file, just the text file you get from your machine, a raw data text file. So we go here and we just am uploading something like here, which is taken in phosphate buffer. And immediately we see that some spectra has come. Okay, now here we can see that we can change the name of my sample. For example, I write here as sample 1 and we can change the concentration and we can also enter the number of residues. Make sure that you notice how your output is coming. Now if you don't want to put this concentration or number of residues, make sure that your output is shown in MDEG, which is the machine file. Like in machine, it is recorded as MDEG. So it will generate as here. But if you want to compare between different samples, it is always advisable to take the MRE, that is the mean residual electricity. And here the MRE is given in millidegree in this unit. So for this, you have to make sure that you have entered the correct concentration of your protein or peptide. And also you know the sequence. If you know the sequence, it's fine. You can enter some sequence. For example, I will write KLVFF, like some amyloid peptides, and some random things, YWYAL, and I press enter, and it is automatically taken into consideration that there are 9 residues, and it has some message for aromatic residues. So if I just remove here, we see it has now 7 residues. Now it is not mandatory to always copy and paste the peptide or rather the sequence. However, if you want, you can manually do it. For example, I know here it is like a 9, it's a peptide which has 9 residues. So I click 9 and suppose I change the concentration from 50 to 200 micromolar. Make sure it is correctly written. 200 micromolar, we see something like this. So this shows that you can immediately get the structure of it without like having the trouble to copy paste and do the blank subtraction. Now one thing I want to show you that here I have taken my sample which is recorded in phosphate buffer, but the other sample has been recorded suppose in SDS. This is the sample 2. So we cannot go with the common blank. So we have to do an individual blank. So once we click here, we have to upload the blank for this peptide here in case of sample 1. In case of sample 2, I will upload a file. Suppose this is my case, I'm giving you an example. But if you have a file recorded in case of SDS, for example, I know I have a file which is recorded in SDS. Now, simultaneously, I have to upload the SDS blank file. Now, this blank upload is an optional thing. You may or you may not do it. I mean, it is of course advisable, but it's up to the user. So now we see that we have two different spectra coming here. Okay, and this two spectra, one is for the phosphate buffer, other is for the SDS. An important thing to note here is that these two spectra are not smoothed, so you can see it's very uneven out here. But another thing is, when I've recorded the SDS spectra, it has been recorded till 195, but it is showing something different here. So we have to make sure that both the spectra have the same starting minimum wavelength. So we can come here in this plot customization range and we can change the maximum and the minimum limit from here. Now, if you want to do a smoothing of this, so we can come here and we can either prefer not to do any smoothing or do any smoothing. Okay, one thing I just want to point out. So here you can see a path length. Make sure you have entered the correct path length, which is also very important in case of your MRE calculation. So my path length, I know 1 millimeter cuvette. So I have written zero point 0.1 centimeter. Now here I have shown you that there are two types of smoothing. One is the FG method and other is the lowest method. So whatever you want, you can apply. Suppose I go to the lowest method, and if you scroll down here, you can see that there is a like a dotted line which is called for the raw spectra, and the other is the smooth line which is for the smoothed spectra. So here you can see the overlap. Make sure that you don't do it like this where your raw spectra becomes very different from your smoothed spectra, but it should be somewhat aligned, like you can understand that it's not deviated too much. So I have these two spectra from here. So, and the next thing is that suppose I am quite happy with it. I know that, okay, I have two samples. I have smoothed it. I did everything. Now you can just come here and in down you can see there are different options. It shows that the DL download the processed plot. Now the processed plot is this one. So if we just download this thing, and you can see an image will be downloaded. So if you open the image, you can see that a very high quality PNG image has been downloaded, which showed you like two different sample names and also a clean spectra. However, if you want, you can also download the raw and the smooth spectra, which is basically a comparison because sometimes you might need to show in your report or in your paper that how much you have smoothed. So here the audience will know that how much smoothing has been done. The next thing is it's not only the PNG image file, but you can also download the PDF file because sometimes people also prefer to go through PDF option and from PDF you can convert it to TIFF or whatever you want. And if you are not satisfied with anything, you can also download a combined CSV file and then you will have the raw and the overlapped like the smoothed spectra, which you can do it in Excel file. So here you can see how easily you can just upload a file. So from this option like sample 1, sample 2, even you can just add one more sample here. Like I can also add one more sample. So here comes sample 3. And in sample 3, suppose I am uploading a different one. Like suppose in sample 3, I upload something like this, just a random thing. And you can see it instantaneously, you get the spectra and immediately you can go here and download the plot. So it's super fast and super easy, and that's the reason why it is called rapid. Okay. And if you zoom in, you can see that your legends are very much like visible, so it's a very high quality image. Now the next thing is suppose you have this, but here you just want to download two spectra. Okay, like you don't want this three, So what you can do from this option where you call the select curves, you can just cross this one. I don't want sample 3. You have this 2 and you can download it. But if you want, you can also keep sample 3. Okay. Now here the option is that it is automatically the colors are selected for the lines, but if you want, you can also go forward and manually select each of these color. For example, here I want to give like a black dark color, so I am giving it something like here. So it's very automated, like you can use it in your own way. I would preferably go with the auto color because these are also quite nice. The next thing is that there is an option called the general analysis tab. Now in this general analysis, there are multiple tabs which you can see. Currently, whatever I have shown is the overlay spectra. Now, if we go to the separate plots, we can find out that in the separate plots, there are three different plots which are coming. So basically, in the overlay spectra, we see three plots in the same overlaid on the same spectra. But if you want to understand or if you want to separate each of these plots individually, so we can just go to the separate plot and we have each individual plot. So you can download three plots together. You can go here and do multi-panel and it will be downloaded like this. See, the resolution is so much intact even after zooming so far. Okay. However, if you want, you can also download each of the spectra one by one, like from the PNG and PDF file. Okay. The third thing is that suppose it is very important for us to know the maxima or the minima because it might be required for many cases. So if you hover your cursor over the spectra, you can see you can understand the minima or the maxima. But however, it is not always very precise and it might be time consuming. So there is an option called the peak analysis. So peak analysis is a very important thing and it is very interesting in the sense that it can automatically give you the maxima and the minima for both. Now the maxima and the minima appears here and you can also download all the four panels together. See, like you have all the maxima, primary lambda minima, you have the lambda minima here and the minima intensities are also shown and maxima and the maxima intensities are also shown. So you have everything. And secondly, you also have this chart like where you have the maxima and the minima value and you can download it as a CSV file. You can save it. So I'm just showing you. Okay. Now interesting thing or rather very important thing I want to share that the maxima and the minima are recorded only in the range which is selected. Now suppose if you select the spectra from 210 to 260 then it will just show between this range. However, there is another option for the peak analysis. For example, in this spectra, there isn't any such maxima as you can see, right? But what happens is that suppose I don't want my maxima to be shown less than 200 because sometimes less than 200 or 195 you can see a lot of spikes or rather I can see a lot of noise. So I want my maxima to be just between suppose 220 to 240. Okay, because sometimes if you go below it might be noise, but if you go to peak analysis it is automatic, it doesn't know like what you want. So you have to specify, suppose if you see that it is detecting something around at very low, like for example it is detecting around like 195 maxima which is might be due to the uh, what we call it, uh, the noise. In that case, you can go here called the peak search. So you can the peak search you can give a restrict maxima. Suppose you restrict it between 210 and 230. If you do that, you can see that it will automatically adjust its the maximum value. Sometimes it might take some time, but sometimes it can do it instantly. So typically it happens mostly in case also of CD spectra where there is noise, or if you want to have like a minima, for example, in alpha helices. In alpha helices, generally there are two minima. If you see that like there are two minima also here, suppose you want to have a minima value for this one, probably the function will select this one. So for sample 2, if we go here, sample 2, we know that the minima is like at 201, right? But we also want to know the minima sometime around this. So in that case, we can manually tell the software to look for the minima between 210 and 220. Okay, through peak analysis. Now, the next thing is the secondary structure. The secondary structure is advisable to follow the general commercially available tools, either like the Dichroism or the best cell. But however, through NNLS deconvolution, in this part, the software can also predict to some extent the secondary structure. So in these cases, the peptide which I am using is not a true peptide, rather a peptide mimetic. So as a result, the secondary structure which it is sort of showing is not correct. It's not accurate. But if you have a correct protein, you might be have an idea about the percentage of secondary structure in it. But it is advisable to go to best cell or Dichroiv. For that reason, we have here an option where from which you can download the file directly, which is the suppose you want like a file for best cell like which you have to upload there. So you can directly go and download a sample file and you can open best cell server from here. So you have an option for best cell also Dichroiv. So you can open here and you can go here and choose the file which you have downloaded. Like I've downloaded this sample file, you can upload it and you can check it from there also. So that is much more reliable, but it has the option. And one of the very interesting thing about this one about the citation. So one thing is quite interesting about the peak analysis is that in case of the peak analysis, there is an option called the literature discovery. So what happens is, suppose you have your minima around like 202, or suppose you have your minima something around 202, and you want to know what papers are there which also has a spectra of CD spectra which have a minima 202. So it serves like some spectra around like some wavelength around this region. And if you go to Google search, it will go into Google Scholar, which have like a minimum like 202, and you can open like these papers and have a look at it. So that helps you to understand like where your peptide is currently standing. We have the secondary structure. Now the next option is now this is the option for similarity. So what is meant by similarity? So if we look here, in this case, we can say that the three spectra doesn't match over one another. Suppose if we have a spectrum in which this red line is almost looking similar to the blue line, then we can say these are quite similar. But here we can say that none of the spectra are matching with one another, but that is like a visual assumption. But if we want to make it much more quantitative, we come here and say that how the spectra are aligning with one another. And through Pearson correlation, we see that only diagonals are having one, that is the highest correlation between these two, between their own samples. But however, if we have look into the correlation between sample 1 and sample 2, then we can say it's 0.51, which is very less, and with sample 3, it's negative, which is far less. So we can also download it as a heat map, and it is also here as a uh, hierarchical clustering or the dendrogram. So, and there is an option how to interpret this chart, so you can go through it. And finally, we have a spectral projection. Spectral projection is basically, if you look into here, you can see how much the depth of your sample is there, like the depth of your plot, and also how much area it is getting covered. So you can do a symmetric like minus 20 plus 20, or you can do an unsymmetric thing from here. So here also you can get a heat map type of thing where you understand that in this region it is much more negative, whereas this region is positive, whereas it is much more positive here in the lower wavelength. So it gives you like an apparent idea. So here also you can download it as a PNG plot and analyze it. So this covers the entire thing about the general analysis tab.